This is lesson 20 of the Quantum Mechanics, a mini lecture series, Waves Part 2. So I'm going to continue our discussion on waves. Just a recap of the idea of superposition. Wave superposition. Superposition means take two waves and add them together, right? Overlap them. Suppose you've got two waves, two pulses on a string, moving in opposite directions. They've got the same size. What you get is a combined larger wave, okay? If, however, you've got two pulses traveling, okay, one is like the reverse of the other, okay, they've got the same height still, same amplitude, I should say, traveling in opposite directions, you will get a cancellation. The top scenario, that's called constructive interference, okay? To interfere means to interact with something. Bottom one, you get destructive interference. Destructive because the waves have basically destroyed each other. Interference. So that's superposition. Now on to the idea of diffraction. Diffraction is basically the bending of light around an obstacle, okay, or the bending of light as it passes through an opening, okay. So here's a simple experiment that was done first. Actually, it's called the double slit experiment. First conducted by Thomas Young, okay, British polymath, Thomas Young, in 1801. Okay, so you've got two slits here, so two gaps, two slits, one slit here, one slit here. And you've got, let's say, an observation screen. This could be a fluorescent screen which glows. Suppose you've got a light source, let's say a light bulb. Okay, it gives out light rays. Now, when the light rays hit the slits act as though they're a secondary source of light waves, okay? It's as though they produce their own source of light waves. And what you see is that the waves coming out from each slit, they interfere with each other. This is a terrible diagram, but I think you might get the picture if you really think about it. Okay, they interfere, they overlap like so. And what you'll get is an interference pattern. This is called an interference pattern. Okay, on the fluorescent screen, so a fluorescent screen lights up when something hits it like a particle. So the peaks correspond to bright spots, and the troughs correspond to dark spots. Okay, so you get a series of dark and bright bands. That's called an interference pattern. Going back to our concept of a wave, picture of a wave. Okay, so it's got a wavelength, distance between two peaks, okay, two crests, or distance between two troughs, okay, two dips. That's the wavelength. And as I mentioned before, if two identical periodic, so periodic means they have this regular pattern. Two identical periodic waves arrive at some point, at the same point, I should say. And they come at the same point out of phase. Out of phase means they're exactly 1/2 wavelength in difference. Okay, in other words, they're out of sync. Okay, so let's suppose one wave looks like that. The bottom wave is like this. It's out of sync, roughly. You will get destructive interference. Okay, because they're not in sync. If, however, they are in phase, okay, top one's like this, bottom one's like this, you'll get constructive interference, okay? They're exactly one whole wavelength in separation, right? And also just a note, calculating the speed of a wave. So V is speed. It's a very simple formula, okay? Usually taught in junior science. Frequency, V equals F lambda. V is the speed of the wave. F is frequency, lambda is the wavelength, usually measured in meters. It's the Greek symbol lambda. Frequency is measured in hertz. Speed is measured in meters per second, usually meters per seconds. You can rearrange this algebraically to get F by itself, divide both sides by F. F's cancel out. So you get lambda is V over F. And similarly, you get F is equal to V over lambda. Right? That's how you can calculate things like speed, frequency, and wavelength of a wave.